Not by smashing through it, just poof, it's there.
Sounds completely impossible in our world, right?
Totally. Like magic. But apparently, down at the quantum level, with tiny particles, this kind of thing can actually happen. Even if the particle doesn't, have enough energy to climb over the wall.
Exactly. It's called quantum tunneling. And for you listening, you've shared some really fascinating sources exploring this very counterintuitive idea.
Yeah, it's definitely mind-bending stuff.
So today, we're going to dive deep. We'll unpack what quantum tunneling really is, why it feels so weird compared to our everyday experience, and look at where this seemingly impossible thing actually shows up.
And it shows up in some surprising places based on these materials, from, like, atoms all the way to stars.
Oh, absolutely. Atoms, stars, even cutting-edge tech. Our mission here is to pull out the core ideas from the info you sent, make sense of it, without getting totally bogged down in, the super heavy math.
Sounds good. We've got to mix this stuff here, explaining the basics, but also touching on some really advanced concepts. So, all right, let's get into it. Quantum tunneling. Where do we even start? Maybe the difference between how things should work classically and this quantum weirdness.
That's the perfect place. So classically, think about pushing a ball up a hill.
Right.
If you don't give it enough energy to get to the very top, what happens?
It rolls back down. Every time.
Exactly. It's stuck on one side unless it has the energy to overcome the barrier at the top of the hill. That's classical physics. Barriers are absolute stops if you lack the energy.
Simple enough.
But in the quantum world, things are different. Particles like electrons, protons, they aren't just little balls. They have this dual nature. They act like particles and like waves.
Okay, wave-like. So not a ball rolling, but maybe.
Yeah.
Like a sound wave hitting a wall. Or a water wave.
That's a really helpful analogy, actually. Think about a water wave hitting a breakwater. Classically, you'd expect it to just reflect back if it can't go over. Right?
Yeah, mostly.
But in quantum mechanics, the description of the particle, its wave function, behaves a bit differently. When this wave encounters a barrier, it doesn't just slam to a halt.
It doesn't, even if it doesn't have the energy to go over.
Even then, a part of this wave, mathematically speaking, actually penetrates into the barrier. And if the barrier isn't infinitely thick,
some of it can come out the other side.
Precisely, the wave function extends through the barrier.
This wave function thing that came up a lot, it's like the quantum blueprint for the particle. Tells you where it might be.
You got it. The wave function, usually written as E, holds all the information possible about a quantum particle's state. Its position, momentum, energy, it's all encoded probabilistically in there.
Probabilistically. Okay.
And the Schrödinger equation is the rule book, the fundamental equation that tells us how this wave function changes over time, including when it meets a barrier.
So the Schrödinger equation predicts this, leaking through.
It does. It shows that even if the particle's energy is less than the barrier's height, the wave function doesn't just drop to zero right at the barrier edge. Instead, inside the barrier, it starts to decay. But crucially, it decays exponentially.
Exponentially. Okay. What does that mean in practical terms? Does it just fade away really fast?
Exactly. Think of it like the brightness of a light shining through thicker and thicker fog. It dims very quickly. The further the wave function penetrates into the barrier, the smaller its amplitude becomes, and it drops off faster and faster.
But not instantly to zero.
Not instantly, and that's the key. If the barrier has a finite width, there might still be a tiny non-zero amplitude left for the wave function when it reaches the other side.
And a non-zero amplitude means?
It means there's a non-zero probability of finding the particle on that other side. It has effectively tunneled through.
So it's a game of chance then, not a certainty.
Absolutely. Quantum tunneling is purely probabilistic. You can't say for sure this specific particle will tunnel. But if you throw, say, a billion identical particles at the barrier,
a certain percentage of them will tunnel through.
Yes. And we can calculate that percentage, that probability. It depends strongly on the barrier's height, its width, and also on the particle's mass and energy.
Okay, the sources had an equation for this decay inside the barrier, something like x ecte to the minus kappa x, that eq.
That's the one. Looks a bit scary, maybe.
A bit.
But the core message is in that exponential. The E is just Euler's number, the base of natural logarithms. The eq in the exponent is the important bit. X is how far you are inside the barrier. Eq, or kappa, wraps up things like the barrier height, the particle's mass, and Planck's that fundamental quantum number.
Right.
So because kappa is positive and there's a minus sign, as x gets bigger as you go deeper into the barrier, that whole eq term gets very, very small very quickly.
The exponential decay we talked about.
Exactly. But crucially, unless the barrier with L is huge, or kappa is enormous, the value when x equals L might still be small, but it won't be zero.
And that tiny value relates directly to the chance of finding the particle on the other side.
Directly. A non-zero wave function means a non-zero probability.
Got it. And looking at how kappa is defined, which involves the barrier height and width, a thinner barrier or a lower barrier should make kappa smaller, right? Which means the decay is slower.
Precisely. Slower decay means the wave function is larger at the far side. So a thinner, lower barrier dramatically increases the probability of tunneling. It becomes much more likely.
Okay, that makes sense mathematically, even if the concept is still weird. Let's talk about where this actually happens. Alpha decay was mentioned first in the sources. How does tunneling fit in there?
Right. Alpha decay is a classic textbook example. Inside the nucleus of heavy, unstable atoms, you have clusters of particles, 2 protons and 2 neutrons, essentially an alpha particle, like a helium nucleus. These alpha particles are held inside the nucleus by the strong nuclear force, which is incredibly powerful but very short range. Think of it as a deep well. But outside this well, the electrical repulsion between the positively charged alpha particle and the rest of the nucleus creates an energy barrier, like a hill surrounding the well.
So the alpha particle is trapped behind this energy hill.
Classically, yes. For many radioactive isotopes, the alpha particles simply don't have enough energy to climb over that electrostatic hill. They should be stuck inside forever, according to classical physics.
But they get out. That's radioactivity.
Exactly. They tunnel out. The alpha particle's wave function extends through that potential energy barrier. There's a small but finite probability that the alpha particle will just appear outside the nucleus, escaping the strong force's grip.
Wow. So the half-life of radioactive elements is basically determined by how likely this tunneling event is.
It's a huge part of it, yes. The probability of tunneling dictates the rate of decay. It's fundamental to nuclear physics, radioactive dating, nuclear power. All rely on this quantum loophole.
It's amazing. Okay, from the nucleus to something engineered. Tunnel diodes. How do they use this?
Tunnel diodes are neat. They're semiconductor devices, but they're built with a very, very thin insulating layer that's our barrier sandwiched between 2 regions of semiconductor material that have lots of charge carriers.
Okay, a purpose-built quantum barrier.
You got it. When you apply a small voltage, electrons don't have enough energy to jump over this insulating barrier classically, but because it's so incredibly thin,
They tunnel right through.
they tunnel right through. This creates a current where classically you wouldn't expect one, or at least not easily.
And what's the advantage of that?
Speed. Tunneling is an extremely fast process, much faster than waiting for electrons to gain enough thermal energy to hop over a barrier like a normal diode or transistor. This makes tunnel diodes useful for very high-frequency applications like oscillators and detectors and microwaves and things like that.
We're deliberately engineering things to take advantage of this quantum effect for faster electronics.
We are indeed. It's a direct technological application of tunneling.
Okay, nucleus electronics. What about the really big picture? The sun. How does tunneling help stars burn?
Fusion in stars. This is maybe one of the most profound examples. Stars generate energy by fusing light atomic nuclei, mostly hydrogen, into heavier ones like helium.
Right, nuclear fusion, ENMC on.
That's the energy release part. But getting the fusion started is tricky. Atomic nuclei are positively charged. What do positive charges do to each other?
They repel
Yeah.
strongly, like trying to push the north poles of 2 strong magnets together.
Exactly. This electrical repulsion creates a massive energy barrier, the Coulomb barrier. For 2 protons to fuse in the sun, they need to get incredibly close enough for the short-range, strong nuclear force to grab them and bind them together.
So they need huge amounts of energy to overcome that repulsion, like incredibly high temperatures.
They do need high temperatures, and the core of the sun is incredibly hot, millions of degrees. But here's the thing. Even at those temperatures, if you calculate it classically, the average energy of the protons isn't actually high enough to reliably overcome the Coulomb barrier.
Wait, really? So the sun shouldn't be hot enough for fusion, classically speaking?
For the rate of fusion we observe, no. Most protons still don't have enough kinetic energy to just smash through the repulsion.
So, tunneling again.
Tunneling saves the day. Even if 2 protons don't have enough energy to climb the Coulomb hill, there's a quantum probability they can tunnel through it. They can get close enough for the strong force to take over, even without classically sufficient energy.
That is genuinely mind-blowing. The sun shines. Life exists on Earth because protons can quantum tunnel through their mutual repulsion.
It's a critical part of the process. Without quantum tunneling, fusion rates in stars like our sun would be astronomically lower. The stars wouldn't ignite or wouldn't shine nearly as brightly or for as long. It's fundamental to astrophysics and, well, our existence.
Unbelievable. Okay, let's zoom back down. Scanning tunneling microscopes, STMs. The sources said they let us see atoms using tunneling.
Yes, another brilliant application. An STM works by bringing an incredibly sharp, electrically conductive metal tip, atomically sharp at the very end, extremely close to the surface of the material you want to image.
How close?
Angstrom's close, less than a nanometer. So close that there's just a tiny vacuum gap, but no physical contact.
The barrier.
Exactly, the vacuum gap is the barrier. You then apply a small voltage between the tip and the surface. Electrons don't have enough energy to jump across the gap classically.
But they tunnel.
They tunnel across the vacuum. And here's the clever part. The rate at which electrons tunneling current is extremely sensitive to the distance between the tip and the surface, like incredibly sensitive. Even a tiny change in distance causes a big change in current.
Because the barrier width changes. Back to that exponential dependence.
Precisely. So the microscope scans the tip across the surface using a feedback loop to keep the tunneling current constant. To do that, it has to move the tip up and down slightly as it scans.
Following the bumps of the atoms?
Exactly. By recording how the tip moves up and down to maintain that constant current, you build up a topographical map of the surface. And the resolution is so good, you can literally map out the positions of individual atoms.
Wow. So we're using this quantum probability effect to essentially feel the atomic landscape.
Yeah.
That gave us unprecedented views of materials, didn't it?
It completely revolutionized surface science and nanotechnology. It was one of the first tools that truly let us see and even manipulate individual atoms, all thanks to tunneling.
Okay, these examples are amazing. But the sources went further into things like quantum computing. How does tunneling fit in there?
Right. Quantum computing is leveraging tunneling in some really interesting ways. One area is called quantum annealing.
Annealing, like cooling metal slowly.
Sort of analogous. Quantum annealing is a type of quantum computation designed to find the lowest energy state of a complex system. Finding that lowest state often corresponds to finding the optimal solution to a hard problem. Now, classically, an algorithm trying to find the lowest point in a complex energy landscape might get stuck in a shallow valley, a suboptimal solution, because it doesn't have the energy to climb out and find the deeper valley.
Like our ball rolling downhill getting stuck in a small dip.
Exactly. But a quantum annealer uses quantum effects, including tunneling, to its advantage. The system can actually tunnel through the energy barriers separating these valleys.
So it can escape the local dips and find the true lowest point more effectively. A quantum shortcut.
That's the idea. It allows the system to explore the solution space more globally, potentially finding better solutions faster than classical methods for certain problems.
Fascinating. And what about Josephson junctions? They sounded important too.
Very important. Josephson junctions are fundamental building blocks for many superconducting quantum computers. The qubits themselves often rely on them. A Josephson junction is basically two superconducting materials separated by a very thin insulating layer or a non-superconducting metal.
Another barrier.
Another barrier. But in superconductors, electrons form pairs called Cooper pairs, which can behave like a single quantum entity. And these Cooper pairs can actually tunnel across the insulating barrier.
The pairs tunneled together.
Yes, it's a coherent quantum process. This creates a superconducting current across the junction with very specific, controllable quantum properties that depend on the quantum phase difference across the junction. These properties are what engineers exploit to build superconducting qubits and circuits.
So the ability of these Cooper pairs to tunnel is essential for making some of the leading types of quantum computers work at all.
Absolutely fundamental.
Okay, it's clearly everywhere.
Yeah.
The sources also gave a more precise formula for the tunneling probability, the transmission coefficient, T equals E to the -2 gamma L.
Ah, yes, TE2L. That's a more quantitative way to express the probability, especially for a simple rectangular barrier.
So T is the probability, L is the barrier width.
What's gamma? Gamma is a factor that depends on the particle's mass. M, its energy E, the height of the barrier V, and Planck's constant. Specifically, it is proportional to the square root of VE times the mass.
Okay, so if the barrier is much higher than the energy, VE is large, or the particle is heavy, M is large, or the barrier is wide, L is large. Gamma gets bigger, the exponent becomes more negative, and T gets smaller.
Exactly. It mathematically captures that intuition. Heavier particles, higher barriers, wider barriers, all make tunneling less likely, exponentially so. It quantifies the sensitivity we've been talking about.
Right. Now, things got even more abstract with quantum field theory and instantons. What on earth is an instanton? Sounds like something out of sci-fi.
It does have a cool name. In quantum field theory, or QFT, we think of particles as excitations of underlying fields, like the electromagnetic field. Tunneling in QFT isn't just about a single particle moving through space. It can be about the entire field transitioning between different stable configurations or vacuum states.
The field itself tunnels.
In a manner of speaking, imagine a field having different possible ground states, like valleys in an energy landscape. The field might be sitting in one valley, a false vacuum, meaning it's stable, but not the lowest possible energy state.
Okay, like being on a ledge partway down a cliff.
Good analogy. Classically, it would just stay there. But quantum mechanically, the entire field configuration can tunnel through the barrier separating the valleys. An instanton is the mathematical solution in QFT that describes this tunneling path, this transition between vacuum states. It represents a trajectory in imaginary time that connects the two starts.
Imaginary time? Okay, that's definitely getting weird.
It's a mathematical tool, Wick rotation, that makes the calculation tractable. But the point is, instantons describe these non-perturbative jumps between field states that are classically forbidden.
And the probability is related to something called Euclidean action, SE. Like P is proportional to e to the minus SE over h bar.
Exactly. The Euclidean action, SE, is calculated for this instanton path. Think of it as the cost or difficulty of the tunneling event for the field. The larger the action, the exponentially smaller the probability of that specific field tunneling event happening.
And one potential consequence mentioned was false vacuum decay in cosmology. That sounds dramatic.
Potentially universe-altering, yes. If our current vacuum state isn't the absolute lowest energy state possible, if it's a false vacuum,
Like that ledge on the cliff?
then there's a non-zero, though likely incredibly small probability that a bubble of the true vacuum could spontaneously nucleate via quantum tunneling, an instanton event, and then expand at nearly the speed of light, converting our region of space to the true vacuum state.
Which would change the laws of physics as we know them inside that bubble.
It could, potentially destroying all existing structures. It's a theoretical possibility known as vacuum instability. Some theories also suggest our universe started after such a tunneling event from a previous false vacuum state in the very early universe, possibly triggering cosmic inflation.
So the structure of our universe might be a result of QFT tunneling.
Wow, okay. And tunneling also pops up in theories of the fundamental forces, right? QCD and electroweak theory.
Yes, in the standard model of particle physics. In quantum chromodynamics, QCD, the theory of the strong force binding quarks.
Protons and neutrons.
Right. There are instanton solutions in QCD. They describe tunneling between different topologically distinct vacuum states of the gluon field. These are linked to phenomena like the theta vacuum and have implications for certain symmetries, like the strong CP problem. It's quite technical, but tunneling is inherent in the structure of the strong force.
And electroweak theory. Weak force and electromagnetism.
There too. In electroweak theory, there are processes mediated by configurations called sphalerons. They aren't quite instantons, more like unstable saddle points on the energy landscape, but they represent the barrier top for tunneling transitions that could potentially violate the conservation of baryon number, protons and neutrons, and lepton number, electrons and neutrinos.
Wait, violate conservation laws? I thought those are sacred. At the quantum level, some symmetries can be violated by these non-perturbative tunneling effects. The probability is incredibly tiny at everyday temperatures, practically zero. But in the extreme heat of the very early universe, these sphaleron transitions might have been important, possibly playing a role in why there's more matter than antimatter today.
So this tunneling is tied into some really deep questions about the fundamental laws and history of the universe. And even black holes aren't immune. Hawking radiation involves tunneling.
That's one compelling way to picture Hawking radiation. You know about virtual particles popping in and out of existence in the vacuum, right?
Yeah, particle-antiparticle pairs, briefly existing due to quantum uncertainty.
Okay, imagine a pair like that forming right near a black hole's event horizon, the point of no return. It's possible for one particle of the pair, say the antiparticle, to fall into the black hole while the other particle escapes.
But how does the escaping one get away? It needs energy.
The particle that falls in effectively has negative energy relative to an observer far away because gravity is so strong. To conserve energy overall, the escaping particle must carry away positive energy. But you can also view the process as one member of the virtual pair tunneling across the event horizon. If it tunnels outwards, it becomes a real particle radiating away, carrying energy. If it tunnels inwards, its partner escapes.
So the black hole isn't perfectly black. It leaks particles via tunneling across its own boundary, leading to evaporation over immense timescales.
That's the implication of Hawking's calculation. Tunneling provides a quantum mechanical mechanism for particles to escape the inescapable gravitational pull, leading to black hole evaporation. It beautifully links quantum mechanics, general relativity, and thermodynamics.
Astonishing. And finally, the sources even hinted at tunneling in string theory, with D-branes and flux compactifications. That's really out there.
It is at the forefront. In string theory, the landscape of possible vacuum states is thought to be incredibly vast and complex. Tunneling between these different vacuas is a key concept. These tunneling events might involve exotic objects like D-branes, higher dimensional membranes, wrapping around extraspatial dimensions, or changes in fluxes background fields permeating space-time. These D-brane instantons or flux tunneling events could potentially allow transitions between universes with different physical laws or different numbers of dimensions, shaping the structure of the string landscape and maybe explaining why our universe has the properties it does.
So tunneling isn't just a particle trick. It might be a mechanism for the universe itself to explore different possibilities within the grander framework of string theory.
That's one of the speculative but exciting ideas, yes. It shows how this core quantum concept resonates all the way up to the most advanced theoretical frontiers.
Okay, let's try and wrap our heads around this. Fundamentally, quantum tunneling is this probabilistic jump through barriers. No classical path, just appearing on the other side.
Driven by the wave nature of particles and the fact their wave function doesn't stop at barriers.
And we've seen it's not just a weird footnote. It's essential for alpha decay, making radioactivity happen. It's harnessed in tunnel diodes for speed. It's literally why the sun burns brightly enough for us, letting nuclei fuse.
Right. And it lets us image individual atoms with STMs. It's potentially a shortcut for quantum computers via annealing and fundamental to superconducting qubits via Josephson junctions.
Then we got into the deeper stuff. Tunneling of entire quantum fields via instantons, possibly driving cosmic evolution or even threatening vacuum decay. Its role within the fundamental forces, QCD and electroweak theory, maybe even violating sacred conservation laws in extreme conditions.
Don't forget black holes seemingly leaking particles through Hawking radiation, interpretable as tunneling across the event horizon.
And finally, its appearance in the complex, multidimensional landscapes of string theory, potentially linking different universes or physical laws.
It really is a concept that spans almost all of modern physics, from the tangible to the highly theoretical.
So for everyone listening, hopefully this journey through quantum tunneling has sparked some real curiosity. It's clearly not just some abstract quantum quirk. It's woven into the fabric of reality.
It underpins processes that shape everything from atoms to galaxies and technologies we're building right now.
It really hammers home that the quantum world just operates by completely different rules than the world we see and touch every day. That intuitive barrier we have in our minds about how things should work, quantum mechanics just tunnels right through it.
Well put. It constantly challenges us to update our intuition about reality.
Which brings us to a final thought to leave you with. It's something as deeply counterintuitive as quantum tunneling particles appearing where they shouldn't have the energy to be is not only possible, but fundamental to the universe. What else are we missing?
What other bizarre-sounding quantum rules might be operating beneath the surface, rules we haven't even conceived of yet?
Exactly. If the impossible can happen probabilistically at the quantum scale, how might future discoveries about these hidden workings completely reshape our understanding of, well, everything? Maybe reality is even stranger, more interconnected, and more reliant on probability and waves than we currently dare to imagine.